Hello. So I've got quite the treat for you today. It's going to be a showcase, and this puzzle absolutely destroyed me. And um, I do have a video of that if you want to see it, where I attempted to live solve this insanely difficult puzzle and did not even manage to place a digit after over an hour. So if you are interested in watching that, you can check the description below. There's an unlisted video just for you if you like to see me fail for an hour. So the reason I made that video is this puzzle is called Little Killer Sudoku by Nityant Agarwal. And he messaged me specifically asking if I could try to solve this. And he hinted that it might be difficult. What I didn't realize is just how difficult it would be and that I'd have no chance at all of being able to solve it live. But that said, it is an incredibly good puzzle, and so once I asked him how to actually solve it, and he walked me through it, I decided I definitely wanted to do a showcase of this. One stipulation that he had was he really wanted to see the video even if I failed it. So I did make that video, I uploaded it. Obviously I didn't release it on the channel because I don't think that's something I want regularly on this channel is failed live solves. But because it's on the channel, I'm going to leave it unlisted, and you are welcome to watch that if you want. So feel free to watch that first if you want. It is over an hour long, so I don't know how much time you have to watch my videos, but you can get an idea of how I struggled trying to solve this. You can also try to solve the puzzle yourself. I definitely encourage you to poke around at least. You may need to reference this video for help, or you may be a super genius and you're able to do it, but I certainly struggled a lot and wasn't really able to make progress. So I think it'll be a treat even just to watch this incredible puzzle unfold. So let me go over the rules first. It is just a Little Killer Sudoku. So if you're familiar with Little Killer, there's nothing more to it. But if you're not familiar with Little Killer, if you notice there are numbers with arrows all along the outside of the grid. What that means is that the cells in the direction of that arrow all the way to the other end of the grid sum to the number next to that arrow. And that's it. And there's no restriction on repeats, so numbers can repeat in cells along arrows as long as other Sudoku rules don't prevent that. So those are the rules. Please feel free to poke around and try it. With my warning that it is incredibly difficult. But with that, I will start going through the walkthrough here. So the first thing we're going to do is take a look at these diagonals here. So I'm just going to bounce around the grid like this. I'm going to start just by, I'm going to start by losing my highlights. So that's a very good start. I'm going to start by highlighting these green, and then I'll change it up a little bit. So if we think about this here, we kind of know the sum of this, but not really, because there's some cells that are double counted. So I'm going to take the double counted cells, which are these here. I'm going to color those blue. So the green ones are single counted and the blue ones are double counted to get our total sum. And I'm actually going to distinguish these cells from the others here. So I'm going to color those purple. So we basically have the 40 sum here, which is blue and green. We have the 13, which is blue and purple, the 34, which is blue and green, and the 15, which is blue and purple. And something you may notice about that is we have two very large sums, which are the ones I chose to be green, and two small sums, which are the ones that I chose to be purple. So what we can do is describe an equation here. So what is the sum of the blue and green cells? So all the blue cells on the board plus all the green cells on the board. Well, that's just the sum of these two diagonals here. So that's going to be 40 and 34. So that's going to be 74. We also have the sum of all the blue and the purple cells, which are going to be these two diagonals. So that's going to be 13 plus 15, which is 28. So I actually have a nice equation prepared here. So we've got the blue cells plus the green cells is 74, and the blue cells plus the purple cells is 28. So if you remember your algebra class, you can subtract these two equations from each other to get another valid equation. So the blues cancel out, becomes 0 when I subtract. I can do green minus purple on this side, and then 74 minus 28 to get 46. So we know that green minus purple is 46. That's pretty huge considering that green is 6 cells and purple is 6 cells. So let's figure out, and that's what this second part of the equation is going to be, but let's just go back to the Sudoku for a second. What is the absolute minimum that the greens could add to? Well, I could have ones in all of them. There's nothing in Sudoku rules that are preventing that. So the greens can add up to, at minimum, they add to 6. So green is greater than or equal to 6. So you can see, I did that backwards, I'm sorry. Purple is minimum 6. I mean, green is also minimum 6, but what we care about is purple. So purple is greater than or equal to 6. And green, at maximum, is all 9s, right? So that's 9 times 6. So that's 54. So green is less than or equal to 54, and purple is greater than or equal to 6. So we can subtract those equations from each other, and we get green minus purple. I suppose they're inequalities, not equations, but green minus purple is less than or equal to 48. So we know that we want them to add to 46. Or sorry, we know that we want green minus purple to be exactly 46. And if we make green as big as possible and purple as small as possible, then they add to 48, right? So we only have 2 degrees of freedom here. We need the absolute maximum in every cell, except we can remove 2. We have to remove 2. So what that means is we either are adding up to 2 to one of the purple cells, or so we're adding 1 to 2 of the purple cells, or 2 to 1 of the purple cells, or we're adding 1, we're subtracting 1 from 2 of the green cells, or subtracting 2 from 1 of the green cells, or we're adding 1 to a purple cell and subtracting 1 from a green cell. Hopefully that's clear, but basically it's 2 degrees of freedom here. So the way I can represent that is none of the purples can ever exceed 3, or we can't achieve our sum. The difference won't be correct, I should say. And for the greens, we also have 2 degrees of freedom, so we can't be less than 7. So this is already a pretty decent start, but I imagine even if you get this far, you might be staring at things and not really know where to go next. So the next thing we're going to look at is this 16 sum, which is a 7, 9. So one of these is 7, one of these is 9. And that's the only way to get 16 in 2 cells with them having to be different. And they do have to be different because they're in the same box. So if we look at this cell and this cell, we can ask the question, can they both be 9? And the answer is no, because if both of these were 9, then this sees this making it 7, and this sees this making it 7, and now we have a conflict. So we know that at least one of our degrees of freedom is used up in one of these 2 cells. We don't know which, but they can't both be 9. So one of our 2 degrees of freedom in all of the greens and purples is used in one of those 2 cells. So what that means is we can only use 1 more degree of freedom in all the other cells. So that means that on all of the purples, we can remove the 3 to remove that 1 degree of freedom. And in these 4 greens, we can remove the 7. Hopefully that's clear. You can go over my explanation again if you're not quite clear on that. But so next, we're going to look at what is the sum of these 5 cells, and the answer is 19. Right? That's pretty clear. It's 10 plus 9 is going to be 19. So the question is, can we exclude a 1 from this 19 in 5 cells? And if you've ever done a lot of killer Sudokus, then you would know the answer is no, because the sum of 1 to 6 is 21. And if we subtract 1 from that, then that's the sum of 2 to 6. So the very minimum without using a 1 would be 2, 3, 4, 5, 6, right? It's 5 different digits in 5 cells because it can't repeat in the box. And the sum of 2, 3, 4, 5, 6 is 20, which is one more than 19. So there's no way we can do that. So we must have a 1 somewhere in these 5 cells. And now we can do something very similar, a very similar trick to what we had before. And I'm actually gonna mark these cells in a different color. I'll use orange. So can all 4 of these be 1? And it's the same thing that happened with this 7-9 pair. If all 4 of these were 1, we would be looking down here from these 2 oranges and left from these 2 oranges, and we'd eliminate all the 1s. We'd in fact be forced to put a 1 in this cell, and we know the 1 is in one of these 5 cells. So another degree of freedom is used up in these 4 orange cells. So that actually lets us place a bunch of digits, because any of the cells that are not part of these 4 must have 1 degree of freedom removed from them. So these 2 purples are now exactly 1. They have no other choice. These 4 greens are exactly 9. And these 2 remove the 7, making them an 8-9 pair. So remember that, and I'm going to remove the highlights on the ones we've filled out, so to avoid confusion. And I'll remove the blue highlights as well to avoid confusion. So we have our orange cells and we have our green cells. And one of our degrees of freedom must be in one of the 2 green cells. And not, it could have been both, but we know it won't be both. But at least one of our degrees of freedom is in the 2 green cells, because we can't do 2 9s because of these 2. And at least one of our degrees of freedom is in the orange cells, because otherwise we'd have all 1s in them, and that would exclude all of these 1s. So what that means is we have exactly 1 degree of freedom in the orange cells used up, and exactly 1 degree of freedom in the green cells used up. So that means the orange cells are 3 1s and a 2, and the green cells are a 9 and an 8. So the question is, can any of these be a 2 or not? So the first thing that we need to notice is that we actually have a 9 placed in this box. And because of that 9, the only way the 1 would be in this 10 sum is if it were a 1 9. So the 10 actually could never have been a 1 there. Or can't now, because we placed this 9. It could have before. And so now 1 is in one of these 3 cells. So if I look at this cell and I tried to make this one the 2, that would force these 3 to be 1. And you can see that this one sees this one sees this, and this one sees this, forcing the 1 out of the box entirely. So it can't be 2, so the only other choice is for it to be 1. So I'm going to mark this one 1, and I'm going to remove the highlight. And so for now, we are going to leave that there. That's the initial break-in. So if you want to try to solve from here, you're welcome to. It's still a very difficult killer Sudoku, even with this. But I think this is a good point to say, hey, if you were stuck, maybe try to get unstuck from here, if you're determined to solve it. Otherwise, feel free to keep watching. So the next step is to realize that we have now limited this 6 here. So the 6 could only have ever been a 1 5 or a 2 4, but we have 2 1s looking in, preventing a 1 from being in either of these 2 cells. So this actually must be 2 4. The other things that we can see is we have 4 9s looking into this box here, and so we can place a 9 in this box. Additionally, something I'm going to point out now, because this is kind of as early as you can see it. Well, I mean, I guess you could have seen it a little earlier, but we were doing the break-in. If we look at this 9 sum here, it's actually not possible for it to exclude both a 1 and a 2. And if you think about it, if it excluded both a 1 and a 2, just like we were doing the 19 sum over here, we would have to add 3, 4, and 5. So at the very minimum, this would be, 3, if I can type the right numbers, 3, 4, 5. And that's quite obviously much larger than 9. That's 12, right? So we have to have a 1 or a 2 somewhere, not both necessarily, but we have to have a 1 or a 2 somewhere in the 9. But we also have to have a 1 or a 2 in this orange cell. So what we can say is that we kind of have a virtual 1-2 pair where one of the one of the 1 or 2 is going to be in the orange cell and the other one's going to be in the 9 somewhere. So I can corner mark 1s and 2s on all of these and kind of say 1 or 2 can't exist outside of those cells. Like we can't have it in these 3 cells. All right, so the next thing to see is that we did place this 1 here, and that does see down here to eliminate this 1 candidate. So now 1 is limited to just these 2 spots in box 7. And so the question is, can this one be the 2? And it's the same process as before. If I put a 2 here, that requires a 1 in these 2. This one sees this one, and this one sees this one. That forces the 1 out of box 7. So actually, what we can say is that this orange has to be a 1, and we can unorange it. And now we have 4 1s looking into box 5, so that should be placeable, and it indeed is. It goes right in the center. So the next thing to look at is, where can 9 go in box 5? Well, we have this 9 looking down here, and this 9 looking over here. So 9 can go in one of these 3. However, what would happen if the 9 were here? Well, if you remember, our greens aren't 8 or 9, they're an 8-9 pair, right? Because we are only allowed to use 1 degree of freedom from these greens, which are limited to these 2. And this 9 sees both of them. So if the 9 were here, then both of these would be forced to be 8, and I'd use too many degrees of freedom. I wouldn't have any for my oranges. So this actually can't be 9. And the consequence of that is we can't put a 9 anywhere else in this row. Because if we did, let's say we put it here, right? If we put a 9 here, that forces an 8 here, and it forces this not to be 9, which then means this is the only place in box 5 for a 9, which again places an 8 here. So it's kind of like a virtual pointing situation. I don't know exactly what to call that, but what that means is this cell cannot be 9. So it is maximum 8. So now what we can do is we can look at what actually is the maximum that this can sum to, because we need to get to 30. So we can have a 7-8 pair here, and we can have an 8 here, because this can't be 9 either. And if we sum that, and now if you look to the top left, I forgot to point this out, but my cursor's there now, to the left of the 34, I actually have a little tiny display of my calculator. So if I'm going to be doing sums, I'm just going to type that in the calculator, and so we'll know that we did it correctly. So in this case, it's going to be 8 times 3 plus 7. So that adds to 31. That means we have 1 degree of freedom from the maximum. So the 8s can only go down to 7, and the 7/8 can only go down to 6. And so now we know we have 1 degree of freedom to take from this. So it's not quite as liberal as any of these candidates. And so the question to ask is, can we get away with not putting an 8 in either of these cells? Or another way to put that is, can this green be 8? Because if this green were 8, it would remove the 8 candidate from both of these. Now, removing the 8 candidate from this cell actually uses our 1 degree of freedom. It makes it 7, and it uses our 1 degree of freedom, which means that these 2 can no longer be 6, and this one must be 8. So that means that either this is 8, in which case, no, this one can't be 8, right? Because there's an 8 seeing it. Or it's 7, and this one's 8. And that at first glance looks okay. But if these are both 7, what do we fill here? This is a 7-9 pair. And now 7's been eliminated from both of the cells. They both have to be 9, and that doesn't work. So because we can't do 7-7 here, we obviously can't put a 6 here without putting an 8 here, because the 6 uses up the 1 degree of freedom. Or they'd both be 8, which is also possible. But either way, there's going to be an 8 here. So that gives us that's huge, right? That gives us this 9, which immediately gives us this 8, and then we can uncolor it because we no longer care. And so now we just have to use 1 more degree of freedom in these oranges. So we'll keep those orange to remember that. This 9 sees down here and actually fills the 7-9 pair down here. The 7 sees up here, eliminating that 7. And also this 9 sees this pencil marked 9 here, so we can actually place this 9. And now these 9s look down into here, and this 9 sees here, and this 9 sees here. So we actually place our final 9 here. So now immediately we've placed this 9 on the 40. We just have one cell left on the 40 sum, so we should be able to figure that out. So we might as well just do a 9 times 3 plus 8 in our handy calculator, and we need 5 more to make 40. And so now this diagonal is pretty restricted with just the 1, 2 here in this cell. So we have 5, 6, 7, and then 1 or 2 more. So we're 8 or 9. So to make 13, we need 4 or 5. And then there's 2 ways we could get this cell here. First, we could do this diagonal. So we have the 9, 10, 11, 12, or 13. So we need 2 or 3 more to make 15. We can check that against this sum as well. So this is 27. We need to make it to 34. So 27 plus 4 is 31. So we need a 3 or a 2 again. So unfortunately, this doesn't resolve, but we made some pretty good progress there. And so the next thing I'd like to point out, which I probably could have earlier, is that one of these 2 cells must be an 8. We already proved that one of these 2 has to be an 8. And now we can also prove that one of these 2 has to be an 8. And it's simple because if neither were 8, we'd have 6 and 7, and we only had 1 degree of freedom left on this sum. And in order to fulfill that, we had to be 7, 8, right? So we'd have to be either 6, 8 or 7, 8, right? We could never have been 6, 7. So 8 is going to be one of these 2. And so how do we do this 14 sum? And the question to ask, since we can't be a 2, is can we have a 1 in the 14, which means that can we add to 13 in 2 cells? Well, obviously we can't be 4, 9 for several reasons. Can we be 5, 8? Well, no, because one of these 2 is an 8. And so the only other option would be 6, 7. But if I put a 6, 7 in these 2 cells, I'd have to put an 8 in both of these 2 cells. So that's not going to work. So I can't have a 1 in my 14. I can't have a 2 in my 14, which means I have to have a 3. So with a 3, I have to add to 11. And so with a 3, how do I add to 11? Well, I can't use a 4, so I can't be 4, 7. I can be 5, 6, and those are the only options because we can't be an 8 or a 9 either. So we are a 3, 5, 6 triple. So we can immediately remove the 6 from these, which gives us the 8 and the 7. So we still have a degree of freedom to work with on these 2. And then 1 has only 1 place to go in this box. And additionally, the 8 sees down here, this 8 sees in here, and we can't put an 8 on our 9 sum because we'd have to have 8 plus 1 plus 0 or something like that, maybe 8 plus 2 1/2. That's not going to work, so we're going to put an 8 here. That 8 immediately sees up here, gives us the 7, and that uses up our degree of freedom, so this must be an 8. And so next, what we're going to do is take a look at this box. We actually know quite a lot about it, especially these highlighted cells here, because the cells are the sum of the 2 little killer diagonals plus the 9, plus either a 1 or a 2. So we can actually figure out what these 2 cells approximately are. So 13 plus 9 is 22, plus another 9 is 31. So we add to 32 or 33. The box itself adds to 45, because 1 through 9 adds to 45. So 45 minus 32 is going to be 13, or minus 33 is going to be 12. So these add to 12 or 13. And we know that the whole diagonal here adds to 27. So 27 minus 12 is 15. So we either add to 14 or 15. Hopefully you followed that there. So how do we add to 14 or 15? Well, we can't use a 9 because the 9s on the grid are done. We can use an 8, but only here. So if we used an 8 here, then to add to 14, we'd use a 6, or to add to 15, we'd use a 7, both of which are possible. If we can't use a 7 here, so we can't do 7 and 7, and that's basically it. There's no other way to get to 14 or 15 without a 9. So this has to be an 8. and this cell has to be a 6 or a 7. So with this 8 placed, we now can look down here, see the 8s, a bunch of 8s are looking in. So this is the only place for an 8, and then we can finish off our 8s by placing an 8 here. And these 8s, sorry, I highlighted way too much there. These 8s see here, and so there's an 8 here. And then finally these 8s, this is the last 8 in the grid. And so now we are done with 8s, which is awesome. All right, so the next thing I want to show is this adds to 34. So if you remember, these two had to add to 7. I don't know if I pointed that out, but 27 is the sum of these 3 9s. So it's pretty obvious that these have to add to 7 to get to 34. So how do we add to 7? Well, we're either going to be 4 3 or 5 2. So if we were 4 3, there's a 4 here, which looks at this 2 4 pair and makes it 2 4 in this way around. Alternatively, we are 5 2, in which case the 2 looks up into this 2 4 pair, making it 2 4 in the same way. So no matter what, this is a 2 4. So now that there is a bit more cleanup that I just didn't get around to doing yet. So that this 1 and 2 here sees down here. So we are actually more limited on where the 1s and 2s can go. Also, we have this 27 sum almost done now. So we will just fill out the candidate there. So we already have 16 for sure. And then the other one's a 6 or 7, and we need to add to 11. So that means that this is a 4 or a 5, depending on if this is 6 or 7. So the next thing I'm going to point out is that this 9 can't actually have a 6 on it. Because if it had a 6, it'd have to be 6 1 2. That's the only choice. But if the 9 were 6 1 2, we wouldn't be able to put anything in the orange, because the orange is a 1 or 2. Because remember, we have a 1 or a 2 in the 9, but not both. So the 6 doesn't go here, and so there's only 2 places that the 6 can go, which is on this 15 diagonal. And so now we can do the sum that we keep doing, or a similar one at least. We know that this is 7 8 9, and then we know that these 3 cells add to 9. So let's just do that sum. So we've got 18 plus 8 plus 7 is 33. So these cells add to 33. With the orange, we're going to add to either 34 or 35, which means that these 2 cells add to either 10 or 11, and they must contain a 6, which means they are a 6 with a 4 or a 5. So that's 4, 5, or 6. Now, if we look at the 15 sum, what that means is that these add to 10 or 11, which means these add to 4 or 5, and they can't include a 1 because they both see a 1. So the only way to do that is with a 2 and a 3. The 4 is going to be 2 2s, and the 5 is going to be a 2 and a 3. So there must be at least 1 2 in one of these. Although I don't think we're going to quite use that. But what we will use is this 2 3 pair that we just created, which eliminates the 2 from here, which means the 1 and the 2 are actually limited to these 2 cells. So that's a hidden pair. So we can get rid of our corner marks and mark that as a 1 2 pair. This 2 3 also sees up here and eliminates that. And so now the question is, where does 3 go in box 9? And so it can't go here because of the 2 3 pair. And if you look at the rest of our marks, they can't go there. So the 3 actually goes in the center cell, which sees up here, which means the 3 must go here in this box. So that's a nice slew of progress there. So the other thing that we're going to look at is this 9 sum now, because we have the 3 placed. So we need 6. So obviously this cell can't be 6, and we only have 4 5 or 6 left. So with a and the 6 goes in one of these 2 anyway. So no matter how you want to look at that, if we want to add to 6, this is going to have to be 1 5 or 2 4. But we have a 4 in the column already, so the only option is 1 5. That places a 2 here. Remember, we kept this orange for a reason. That means this one must be 1. Now we can finally get rid of all of our highlighting. And I believe that, yeah, so now this 5 sees up here, so we can do 6, 5. This 5 sees back down here, and I guess we could have done that from the box as well. And so now we know this is 4, 6, and so now we know these two have to add to 5. But we don't quite know which way they go yet. We can fill out the 4, 5, 6 that's left here, and this one can't be 5. And so now you may have noticed that we actually have 4 out of the 5 of this sum here. So we're actually going to be able to finish the whole diamond. So we need 13, and we have 8. So that means we need a 5. And then over here, we have 27 plus 5, which is, this is why I use a calculator to make sure I don't get this wrong. So that's 32. So we need 2 more. So that makes this one a 2. And so now that also, if we had just looked at this diagonal, should have given us the 15 as well. Let's just double check that. So we have 10 here and then another 5. But placing that 2 here places a 3 here. And we know this has to add to 5, so that places a 2 there. Next, we did place this 1 a while ago, and we didn't clean that up either. We also have this 1 here, so I have multiple 1s looking at this. So this is a 1. And what we can actually do is do this sum now. So we know what the sum of all these cells are, so we should be able to figure out what the sum of the remaining 2 cells should be. So these add to 19, and then we have another 17. So those add to 36, which means we need another 9 in these 2 cells. So how are we going to make 9? Well, we can't do 1, 8. We can't do 2, 7 because this 2 and this 7 see. Sorry, let me highlight these cells so I can highlight other stuff too. This 2 and this 7 see this 1 cell, so we can't do 2, 7. 3, 6 would be required to be this way, 6 and 3, because we have this 3 seeing here. And then 4, 5 is impossible because, oh, sorry, it is possible. What am I saying? But it's only possible in this direction. It would be 4 and 5 like that. So let me just, I'll leave those highlighted until we figure out what they are. So we remember those have to add up to 9. And so now the question is, how do we make this 10 sum? So we can't do 1, 9. We can't do 2, 8. Those should be obvious. We can do 3, 7. But if we did 3, 7, then we'd have to do the 7 here and the 3 here because of this 3 and this 7. So 3, 7. Can we do 4, 6? And the answer is yes, we can do 4, 6. And obviously we can't do 5, 5. But if we did 4, 6, that would remove the 4 here and the 6 here, making these add to 8. But we know they have to add to 9. So they're not 4, 6. So that actually places the 7 here and the 3 here. And the 3 makes this a 4 and a 5. So that's pretty fun. The remaining here have to add to 8. We can tell that in several ways. And they have to add to 8 by being 2 and 6. And this 2 C's over here. So that's 6 and that's 2. It also, we could have just used normal sudoku for that, but okay. So now there's only 1 cell left in this row. That's going to be a 5. And then this 24 we can finish. This adds to 18. So we need another 6. So this one is a 6. That 6 is over here. And remaining up in this column here, we need a 2 and a 3. So the question is, with this 9, if we were a 2 or a 3, what would this one be? So if we're a 2, then we're a 7, and if we're a 3, then we are a 6. That makes a 6, 7 pair here. That gives us this value here, which is the missing one, which is a 4. And so that places a 5 here. And this 13, we have a 4 and we have a 2 or a 3. So we need 9 with a 2 or a 3 And we have a 6 or actually an even easier way to do this. Sorry, we have 2, 3 used. We need 6 or 7 left in the box. The 7 C's here. So this is 6, this is 7, this is 6. We can do this sum now, so that's 2 and that's 3. And just to make sure, 6 plus 3 is 9, plus 4 is 13. So there are probably several ways to finish off that box. And at this point, the puzzle is basically broken. I mean, broken in the way that it's pretty trivially solvable at this point. There really aren't even that many sums left to do. But I will continue, just so you can see the nice ending to this. So this cell is missing the 4. That 4 C's over here, so that makes this 6. Leaving a 4-5 pair, so this one is 6 and this one's 4. There's only one left for this row, which is a 4. And then now we can take a look at this 28 sum. So we've got 12 plus 4 is 16, plus 2 is 18, so we need 10. So how do we make 10? Well, we know it's not going to be 1, 9, or 2, 8, because all our 9s and 8s are used. So we can be 3, 7. And if we were, then it would be this way. 4, 6 isn't possible because there's a 4 in both of these boxes, or 5 and 5, but this cell sees a 5, so it can't be a 5. So that actually just leaves 3 and 7. And so now for this row, we also need a 3 and a 7, so that should be pretty clear how that goes, 3 and 7. And then this column only needs a 2. And this row needs a 6 and a 7. And the 7 C's here. So this is 6, this is 7. This row's been done for a while. It's a 3. In this row, we need a 2, 4, and 7. And the 7 and 4 look up into here. So this is the 2. And then the 7 C's here. So this is the 4 and this is the 7. And just finishing up, we need a 2, 5, 4 for this row. Neither of these can be 2. So this is the 2. This can't be a 4. So this is 5, 4, 5. And then finally, just to finish these columns, we need a 3, a 6, and a 4. And we actually solved the puzzle. Well, I showcased it at the very least. So again, if you want to watch me struggle for an hour getting no progress in this puzzle and doing it completely wrong, there is the unlisted video in the description. Otherwise, I do have a bunch of other videos on this channel if you haven't seen them all. I do other showcases of crazy difficult puzzles that I could not have solved myself, but I found extremely interesting. Some of them are ones that I did solve, but I solved them not live on video, but I still wanted to showcase them, so I did that as well. I also do live solves on the channel. And when I succeed at actually solving it, it goes up on the channel. And so those can be fun as well. You can yell at the screen as I miss a bunch of stuff. And I also have a Learn to Love Sudoku series, which is especially nice for people who are just, as the title might imply, who are new to Sudoku and want to get into it and want to learn what all the hubbub is about. So it assumes that you know nothing about Sudoku from the start, and it very quickly introduces advanced concepts in a way that are both understandable as well as fun to do. And there's packs of puzzles in there. I think at this point I've released about 50 puzzles in that series, in just 3 videos of that series. I mean, maybe it's 45 puzzles, something like that, some crazy number. And I will be continuing that series and releasing more. So check all of that out. If you like my videos, make sure you subscribe. That's good for you. It's good for me. Everyone involved benefits. So please do that. And other than that, I hope you enjoyed the video, and thank you for watching.